Let's start with what actually breaks. You've got a single Postgre or MySQL node. As traffic grows, you hit three limits: connection pool exhaustion, IO throughput ceiling, and log connection on write heavy tables. The typical first move is vertical scaling, obviously. We try to get a bigger machine, more RAM, faster drives, so that buys you time, but it doesn't solve the architectural problem. At some point, one machine cannot physically handle your write throughput, and that's the forcing function for sharding. So remember it this way: sharding is a horizontal partitioning of data across independent database nodes. So each partition is a shard, like it's a fully autonomous database instance with its own storage, compute, and connections. So the data is split using a shard function. In this example, we have user ID modulo 4. So user 1001 goes to shard 1, user 1002 goes to shard 2. So crucially, unlike replication, each shard holds a distinct subset of the data. There's no overlap, and together all the shards represent the complete data set. So shard key selection is the decision that's the hardest to reverse and the most expensive to get wrong. A sequential integer like auto increment user ID sounds natural, but it means new writes always concentrate on the latest shard. Hashing the key gives you uniform distribution, but you lose the ability to do range queries efficiently because consecutive values are now scattered across shards. Tenant ID works well for B2B SaaS, where isolation per customer matters. Geographic sharding helps with data residency laws. The rule is the shard key should map to how your most common queries are scoped. Also, a hotspot is when your shard key has low cardinality or skew distribution. So one shard absorbs disproportionate traffic. If you shard by account type and 80% of users are on free tier, that shard handles 80% of your writes. So you've scaled horizontally on paper, but vertically in practice. This also happens with time-based keys. If you shard by created at date, current day writes always hit the same shard, right? So the fix is either consistent hashing or either adding an entropy to the key, like hashing user ID rather than using it raw. See, we know for a fact that naive modular hashing has a serious problem. Adding or removing shards remaps almost all of your keys. We have discussed this problem in the video of consistent hashing. Like, I'll leave the link of the video in the description below. Check it out if you are interested. If you go from 4 shards to 5, user ID modulo 5 produces completely different results from modulo 4. That means you would need to migrate most of your data. Consistent hashing solves this. You place both shards and data keys on a circular ring using a hash function. Each key is assigned to the nearest shard clockwise to the ring, and when you add an extra shard, only the keys between it and the predecessor need to move. Roughly, it would be around 1 by nth of the data, where n is your shard count. And this is how Cassandra and DynamoDB all handle it internally. And also, your application can't just fire queries into the void, it needs to know which shard to talk to. There are two approaches. One is application level routing, where the app itself contains the shard logic and talks directly to the right database. Or we also have a proxy based routing layer that sits between your application and your databases. So the proxy passes the query, extracts a shard key, consults a shard map, and forwards a request. Vitess does this for MySQL. It's how YouTube scaled their databases. The advantage of the proxy logic is that your application code stays clean and you can change your sharding topology without touching the actual application logic. This is a core architectural trade-off with sharding. Queries that include the shard keys are fast, that is, the router forwards to exactly one node. But queries that don't include the shard key or that aggregate across dimension that don't align with your shard key require a scatter gather, that is, you fan out to every shard, collect all partial results, merge them in the memory, and return. That's n work round trips, n query executions, and a merge step. For analytics or reporting workloads, this gets expensive really fast. The common pattern is to run a separate read replica or data warehouse for cross shard analytics, so you don't pollute your transactional shards with scatter gather queries. And also, at some point, your shards themselves get too large and you need to reshard again. So you go from 4 to 8 and 8 to 16. This is operationally complex and it's one of the reasons teams over provision shards upfront. A typical resharding process involves dual writing, that is to both old and new topology simultaneously, backfilling historical data in the background, verifying data integrity with checksums, then cutting over reads and finally writes. The whole process can take weeks for large datasets. Tools like Vitess have built-in online schema changes and resharding workflows that automate parts of this, but it's never trivial. And also, asset transactions across shards are genuinely hard. Within a single shard, your database handles transactions normally, but if a transaction touches data on two different shards, you need a distributed transaction protocol, typically two-phase commit. Phase 1 will be both shards acquire locks and confirm they are ready to commit. Phase 2 will be the coordinator that tells them both to commit. The problem is failure scenarios. That is, if one shard goes down between phases, you have got partial commits and locked rows. The latency overhead is also real, and most high-scale systems avoid cross-shard transactions entirely by designing their data model so related data lives on the same shard. These three get conflicted constantly, so let's be precise. Replication copies the same data to multiple nodes, it improves read throughput and gives you failover, but every write still goes to one primary. Table partitioning splits a table into logical chunks on the same database instance. For example, we have Postgres range partitioning. It helps with query pruning and maintenance, but doesn't distribute write load across machines. Sharding distributes data across independent nodes. That's the only one that actually scales writes horizontally. In production, you use all three. Each shard has its own replicas, and within each shard, you might use table partitioning on large tables. Let's look at Vitess as a concrete example because it's open source and widely deployed. VT-get passes the query, figures out the shard key, and routes it to the right VT tablet. VT tablet is a sidecar process that runs alongside each MySQL instance. YouTube built this internally and open sourced it. Slack also uses it. The key insight is that your application literally doesn't change. It still writes MySQL standard queries, and Vitess handles all the distribution underneath. Before you shard, work through this sequence. Is your bottleneck reads? Replicas in a caching layer like Redis will fix that without complexity of sharding. Is it slow queries? Proper indexing, query optimization, and connection pooling first. Are your writes genuinely bottlenecked after all of that? That is sustained 50,000 plus writes per second or database sizes above a terabyte on optimized hardware? That's when sharding becomes justified. The operational cost is real. That is, you're adding distributed systems complexity, losing cross shard transactions, complicating your deployment and monitoring. Most applications at most companies never hit this threshold. Shard when your metrics force you to, not when it sounds architecturally interesting. Now to close, sharding is horizontal data partitioning across autonomous database nodes. Your shard key is your most consequential design decision. That is, it determines distribution balance and query efficiency. Use consistent hashing to keep topological changes manageable. Design your schema so your common queries are shard local and avoid scatter gather. And treat sharding as one layer of stack that includes replication and partitioning and not a standalone solution. Thanks for watching. I'll see you in the next one.